Welcome to the third lecture on power and temperature management. So we'll first look at power management and then get into temperature management. So the most popular method of managing power is called voltage frequency scaling. Rather, it's called dynamic voltage frequency scaling or DVFS. So what happens is that as we have discussed, the voltage and frequency have a relationship. It used to be linear, not anymore. So then what is the relationship between this and this? Well, the relationship between this and this is, so voltage is some function of the frequency. And in general, increasing the frequency means you have to increase the voltage almost all the time. So most processors, as you can see from the Intel Pentium M processor, they have a table. It's a voltage frequency table or DVFS table that given a frequency, what should the voltage be? If it is 1.6 gigahertz, then what should the voltage be? 1.484 volts, so the supply voltage, and again 0.6 gigahertz, 0.956, so on and so forth. So recall that we had discussed this relationships threadbare in lecture 1. This is lecture 3 at the moment, right? So lecture 1 of the same slide set on power and temperature. So then who decides, who makes these decisions of when to change the voltage and frequency? So this can be done by hardware in the sense when it sees it's heating up, it can reduce the frequency, or when it is seeing less activity on the CPU, it can reduce the frequency. Or it could be software controlled where the OS gives a direction to the hardware to reduce or increase its frequency. So the CPU FREC utility on Linux actually does that. So that is software control. So every chip has a power grid and a frequency regulation system. So we have a 3.3 volt power supply typically, and a voltage regulator that provides voltages in the range of zero point 0.8 to 1.2 volts. And then again we have a quartz clock. So the quartz clock will generate a fixed 133 megahertz signal, and the PLL is kind of is a frequency multiplier on top of this quartz clock. So this multiplies the frequency, hence you can't like scale it to an arbitrary frequency, but you can scale it to different multiples of this 133 megahertz as the PLL is set up to do that. So the PLL provides a frequency base and then a voltage base is provided with the voltage regulators. They could be on chip or off chip. Most of the time they are off chip, but the PLLs could be on chip though. So then the idea is that if you want to generate any frequency, you need to tell the PLL that look, I want to generate 2.13 gigahertz. So this is 133 megahertz times 16. So you essentially do a frequency multiplication with the factor 16. So it will do that, and of course distinct factors are possible, arbitrary factors are not possible. But then what happens is that to go from let's say one frequency to another frequency, the PLL needs to relock. Relock basically means that it will temporarily stop, then try to generate the new frequency. This process will take several adjustments. Finally, the PLL will converge or lock to a frequency, and then it will keep on generating that frequency. But during this time, the chip is unusable. So this is known as a PLL locking time, and the PLL is known as a phase lock loop. So what happens is that let's say I want to change my voltage and frequency. So I keep on operating, and let's say I want to go from voltage V0 to V1. So first I increase the voltage. After I have done that, I tell the PLL to increase the frequency. So the voltage can always be increased. There's no issue in that. But to increase the frequency, you need a higher voltage. That's the reason we increase voltage first. Once our voltage regulators have done their job, for this period of time our processor is not usable, typically 10 to 20 microseconds. Then there is a steady state, and the steady state continues. And then what happens is that my voltage again goes down. The steady state in terms of voltage, right? Not in terms of frequency. And then what I do is while reducing, I again bring my frequency down. That can be done. So while bringing the frequency down, I need not bring the voltage down. I can bring it down later. So again, I bring my frequency down, and then again I bring my voltage down and continue. So as you can see, I always increase the voltage first. That is needed, and then I increase the frequency. While reducing the frequency, again I reduce the frequency first and then I reduce the voltage. So let's now look at hardware based DVFS. So what we do is that we estimate the amount of CPU activity, which is not a very hard thing to do. So we can look at the IPC, we can look at the usage of different functional units. So if it is low, then we can reduce the frequency because we are not using the CPU a lot. So maybe we are doing a lot of IO. So then why do you need high frequency? If it is high, then most likely you are doing something which is important, which is CPU heavy. You would need high frequency. So well, why not increase it? So again, these are a conflicting set of requirements. Okay, so this set of requirements over here are conflicting. Look at the power and temperature. If both are low on the lower side, then it makes sense to increase the frequency because you can get better performance. But that would depend upon whether increasing the frequency will help or not. If both of them are high, then you have to reduce the frequency because you don't want a high power scenario or a high temperature scenario to continue for long. Right? So this is the broad philosophy of any hardware based frequency control, where you look at a bunch of requirements which may actually be in odds with each other, right? They may be conflicting. How would they be conflicting? Well, it's simple. It could be that, as I said, you may want to increase the IPC further, but the temperature is high, hence you cannot increase the frequency. So, of course, whatever decision is taken has to take into account the actual power temperature realities and the CPU activity. Software based DVFS can easily be done. So, a lot of processors expose instructions for the OS to actually change the voltage frequency setting. So video is a quintessential example. So if you're looking at 30 frames per second, 30 FPS video, which means that one frame needs to be processed in 33 milliseconds. Assume that we can process a frame in 20 milliseconds. Then clearly there is a 13 millisecond slack. So why have such a large slack? What we can instead do is that we can reduce the frequency. So then what will happen is that we will reduce power also. And as we have seen, a small reduction in frequency is a big reduction in power. But of course, we need a method, a model, a formula to relate the processing time, which is this 20 milliseconds, with the frequency. So now, if we look at regular programs, so if you can classify them as hard real time, means strict real time constraints. Soft real time means even if you violate a constraint, it is fine. Interactive, we know, something like a game. Periodic would be a periodic task like this, again, video processing, that once every 33 milliseconds you need to process. And then batch is something which runs in the background. You don't really care when it finishes unless it takes very long. Then we can have, based on the classification, different policies. For real-time tasks, we have to set the DVFS settings such that the deadline is being met. As long as the deadline is being met, there is no need to increase the frequency any further. Interactive jobs, well, we'll have to look at what is called the quality of experience of the user. If it is high, well, don't increase the frequency, consider lowering it. If it is low, consider increasing it. Again, periodic jobs like this, take the periodicity into account and see if we are completing before the deadline or not. And batch jobs, well, look at what are the requirements. In many cases, a batch job would be, go and compress some database or some file or something, or a set of files, or run a script on a bunch of files. So you don't really care how long it takes. If you don't care how long it takes, let it take a long time. What's the issue? So Linux has a CPU frec utility, which is also known as a speed governor because it governs the speed. So what the CPU frec utility does is that it has different policies or different settings. And because Linux is a general OS, it runs on all kinds of processors, so it cannot really have anything which is processor specific. And even for Intel AMD, different processors have different DVFS settings. So you would want Linux to kind of have the flexibility to map a high level thing to actually a low level thing like a voltage or frequency. So performance is maximum possible frequency. So this is clear. Power save is minimum. Again, this is clear. This is the other side of the extreme. On demand is basically that you set a constant rate of CPU utilization, and if it increases, well, then increase the frequency such that the CPU finishes its job sooner. So this of course uses a set of thresholds in the sense that, you want the CPU utilization to sort of be between these 2 points. So then the OS will work with the processor and keep setting the DVFS settings accordingly. Conservative is again a version of the on-demand, but slightly more on the conservative side, as the name suggests, nothing more to add here. So then interactive actually relies on the formula that we were talking about, where the CPU utilization is being related to frequency, because look, it's not very clear. Sometimes even if the CPU utilization is low, you would want that low part or whatever you're running to run as quickly as possible, such that some other entity like an IO device or something can actually uh, get the data faster. Sometimes you have low CPU utilization because of high memory miss rates. In that case also it's an issue because in lowering the frequency doesn't really help. So the relationship between these for an application need to be understood, and the OS either has to create a model or the programmer has to help. But in this case, Linux tries to create some model of its own. And based on that, it tries to provide a good quality of experience where it has some heuristics with respect to what constitutes a good quality of experience. So this it would apply for purely interactive jobs, right? So of course it can do there are other tricks up its sleeve, like increase the process priorities and so on at the OS level. But since we are talking of DVFS, which is voltage frequency scaling, we can use, as I said, a bunch of thresholds, which are these two, where you say that, look, we want the CPU to be utilized this much to this much, right? Maybe 80 to 100% of the time, or 50 to 70% of the time, and then it will ensure that whatever work it has, this is how much the CPU is used. But interactive would use a formula, so it's slightly sophisticated. And the other two are simple extrema. So I hope that these five are clear. So keeping this in mind, let's move forward. So DVFS was a simple mechanism. Hardware can do it, software can do it, right? Both can do it. And this is a very old idea. It's not a new idea by any measure. It's not a new idea. Now here is the fun part, that we can do more. So what we can do is that for dynamic power, what we have seen is if there are no transitions, which means if there is no 1 to 0 and no 0 to 1, if no transitions means no power, because there is no voltage transition, right? You will still dissipate static power, but you won't dissipate dynamic power. So dynamic power is purely dissipated via voltage transitions. And the best way of stopping these transitions is that you simply disable the clock. So if this is the clock, you AND it with the clock gating signal. If the signal is 1, this is 0, the result is 0 regardless of the clock. And if the clock gate is 0, then this signal is 1, which means that the output here is the clock, which basically means that when you feel that your circuit is not going to work, that you would know. For instance, if you are running integer instructions, then your floating point unit will not be used. If you are running floating point instructions, your integer unit will not be used. So this is known to the processor, at least the earlier stages, what will be the usage of later stages. So this information can be properly conveyed. You can have software support as well, but that would be too much because a lot of hardware details will have to be exposed to software, which is in general not a good idea. So what we can do is that we can gate the clock, which means set the clock to 0 by setting the clock gate signal to 1. And then basically no clock, no transitions, no dynamic power, right? So essentially it's a negative edge triggered scenario. Whatever is there in the latch at the inputs prior to the negative edge gets transferred to the outputs. And then this leads to a bunch of transitions throughout the logic part of the pipeline. But this is not going to happen because the clock is disabled, so there is no movement. Of course, how do you predict is an important thing. You can use past history, or you can look at what is there in the decode stage and try to make a guess, try to forecast. So this is difficult, but clock gating again is an industry standard now. There are a lot of correctness problems. The first is that verifying such circuits becomes very hard, very tough, very difficult. So in a lot of designs, the designers explicitly want that regardless of clock gating, either with clock gating or without clock gating, the internal states of all flip-flops should be the same. Otherwise, verifying will become very tough and very difficult, and the internal state is going to become very difficult to verify. That's the reason you have to somewhat make conservative choices and say that, look, you can clock gate as much as you want, but anytime I verify, the state should be indistinguishable from the scenario in which there is no clock gating. It clearly introduces spurious clock edges because if the clock is 1 and you're gating it, you're then kind of enforcing a 1 to 0 transition, which is early. This may cause faults in the circuit because clearly the circuit is not expecting that a transition will come early. So if you want to gate the clock, you gate the clock when it is at level 0. That's the safest. Then the level 0 is going to continue. Clock gating example, we all have seen a carry look ahead adder. So if bit number 4 changes, right? So then carry look ahead adder idea is simple. We propagate some information here and then we again propagate some information back, and that allows us to do the addition. So bit number 4 changes, its entire path. So there's a tree in reverse basically. From here to the root, the entire path will see transitions. So this part in red will see transitions, but the rest of the elements will not see any change. So they can be clock gated. This is one example. There can be many such examples. Of course, this is an example within a functional unit. You may argue that this is too fine-grained a level, and I will not contest that. But in general, it's a better idea to do it at the functional unit level as opposed to intra-functional unit level. Other simple ideas, issue and fetch throttling. So clearly there's a power versus IPC trade-off. As you do more architectural tricks, you spend more power. So the fetch rate, issue rate, commit rate, essentially how wide your processor is, can be dynamically adjusted. Saying instead of issuing 6 instructions per cycle, I will issue 4. That will bring down your power automatically. Of course, it will bring down your IPC, but you need to make a trade-off. The entire thing is about trade-off. So, of course, you may argue that, let's say, for a given benchmark, if this is the issue rate and this is the IPC, and let's say I have a second axis which is power, then you can say that, look, initially the IPC is kind of low, but as the issue rate increases, IPC becomes like this. Similarly, for power, you can say that, look, initially the power is quite low, but As I increase the issue rate, it kind of goes like this, right? So then you can say that, look, maybe, a good point to operate is somewhere here. You can, right? So this of course depends on other factors like temperature and battery budgets and so on, but uh, an argument can be made. So we can plot the IPC with the issue rate and say that, look, as we increase the issue rate, IPC increases, power also increases. What do I consider to be a nice and safe point? This is a decision that architects have to make based on other considerations. Now let's look at leakage power. So leakage power is not the same as dynamic power. This is based on, dynamic power was based on transitions. Leakage power or static power is dissipated statically. And it is basically based on the fact that interfaces are not ideal, so current leaks out. So what's the idea? Simply turn off the supply, as simple as that. So disconnect the connection between either the silicon layer and the power grid. So we have a power grid. So what happens is the way that the power is provided to the circuit is basically you have this grid like shape, and every grid point basically provides power here. So the idea of having a grid is that you can nicely balance the power. So if let's say there's a high power draw here, current can flow in via different directions over here. If there's a low power draw here, then the reverse effect will happen. But the idea is you have a power grid and we have connections to the power grid for different functional units. So we can have these, decoupling transistors here known as sleep transistors. And it's a transistor is after all a switch, right? So you can just open the switch. So this will get disconnected from the power grid. Basically no power, no leakage. There is nothing to leak. Similarly, instead of the power grid, we can turn off the connection of the ground grid. So then current will not flow. Or we could have two decoupling transistors on both sides and then turn both of them off. So then this layer will become fully floating. It will not be able to get any power. So the idea here is simple. If we turn this off, then basically, and also this off, then this becomes an open circuit. So there is no way that current can flow in here other than the tiny amount of leakage via this transistor, which is minimal. This is minimal as compared to all the transistors in this functional unit leaking, which is actually much, much more. So the key idea is that we create these islands of transistors like this. This is an island, this is an island. Each island is connected to both to the ground grid and power grid, and we have these transistors. So what we do is if we disconnect them, current doesn't flow and no current flows, so basically no leakage. And this is known as power gating, which is done, but it is expensive, as we shall shortly see. There are a bunch of issues we have to keep in mind. So many issues, I just listed them down. So the idea is that the current that is being sent to these functional units, right, should not uh, reduce, right? Because what would happen is that the transistor itself would have a certain current carrying capacity, it would have a resistance. So the current and voltage, etc., should not reduce. So you have to look at what current is still available to the functional unit. It should roughly be as it was a direct connection, right? So this transistor has to be really wide. The sleep transistors themselves can take time to switch on and off because they are large transistors. They would have large capacitances associated with them. So if let's say they take a fair amount of time to turn on off, then during that time the system is unusable. So we'll have to take that into account. So clearly, unlike clock gating, power gating cannot be done at a very fine granularity. It can't be done very quickly. So we'll have to figure out larger uh, quanta of time. For instance, we could have coarse grained partitioning, like if at the level of a full core. If a core is not being used because the OS has not given a task to it, then we can power gate it. So as I said, there will be some leakage via the sleep transistors. That is not much. If I were you, I won't consider it. The key problem, I would say, the reason that this is in red is because there will be very, very abrupt changes to the current that is either flowing into an FEU via the power grid or the ground grid. So there will be very, very abrupt changes because you are disconnecting a large circuit. So this will have fundamentally a destabilizing effect over the grids. It will cause these current pulses, and these current pulses may go and destabilize other functional units that are connected. That may cause faults, as we shall see in the next chapter. So the right way of doing it is to sort of do it at a time when the system is not used a lot, or add these decoupling capacitors which will be able to absorb those spikes, right? But large capacitors are required. Otherwise, the destabilizing effect may actually flip bits, which is something that we don't want. So this process of power gating a circuit or unpower gating is problematic, and you have to design this part very carefully. So again, sleep transistors, same problem as the first, reduces both current as well as the voltage, and furthermore you have to predict in advance, similar to clock gating, but in this case you are predicting for a larger duration of time. And finally, when you power gate something, it loses its state. So you clearly don't want it to remember something that you would use later, because the moment you power gate, anything that you had stored is gone unless it is stored somewhere in memory. So these were a lot of issues, right? But that doesn't mean that it is not done. It is done. But again, with these riders or caveats. Now we can look at something else which is, I would say, it's a part of the standard practice. So let's look at some things. Transistors that have shorter channels and transistors with longer channels, right? So if a normal transistor is a rule of thumb, it takes 1 unit of power and time is 1 unit. A long channel transistor clearly will be slower, but not very slow, right? So recall that, even for a small amount of performance, we can spend a lot of power. So essentially, it will be significantly more power efficient. Of course, this is for current day technology, 2021, 22. I'm not sure about the future. But again, if the channel is very long, it's going to be 0.3 units. So you'll save a lot of power. And the performance loss will be little, but depends on the design. So what you can do is that you can have normal transistors on the critical path for speed and slower transistors off the critical path to save power, which is a standard technique. So then what will happen is that we will not perceive the fact that they are slow because they are not on the critical path anyway. They are not determining the timing. Similarly, along with the channel length, gate sizing, so the delay is typically looks like this: A plus B by W, where W is the gate size, gate width. Sorry, width of the transistor, I'm sorry. Yeah, so larger is the width of the transistor, lower is the delay. For obvious reasons, it's bigger, so it can store more charge, it can affect transitions faster. But wider it is, more is the power. So then, if you have a slow transistor, you'll have a smaller W by L ratio, faster one, larger. So it's a rehashing of what I just said, but the idea is the same, that you have slow transistors off the critical path. So this saves power. You have faster transistors which are on the critical path, which gives you the performance, right? You have very, very fast transistors which are on the critical path for performance, which would be the ones with, as I said, larger width, but in this case you will be dissipating power. In other case, you trade off delay for power in a different direction. Another such idea, which is adaptive body biasing. So we will see all of these things in the next chapter as well, in a slightly different avatar. And here the threshold voltage VTH of a transistor is of course a function of the supply voltage and the body to body to source voltage. So what happens is, if I increase the VDD, which is the source voltage, right, then I can kind of bring the threshold voltage down. If I bring the threshold voltage down, I'll increase my leakage power but increase the speed of the transistor quite a bit, because in this case, to actually change its state, I don't have to charge much, right? My threshold voltage is lower, hence the transition is faster. Similarly, if I tinker with this body voltage, I can also lower or increase or decrease my threshold voltage, which will give me a performance benefit, or take you in the reverse direction where it will make the transistor slower but more power efficient. So forward body biasing is when we increase VBS, this will reduce VTH. Needless to say, it will increase performance but also increase leakage power. Right here we are. Similarly, if we do reverse body biasing, which is decrease VBS, it will increase the threshold voltage, but it will reduce the leakage power, reduce the switching speed. So this is again one more knob that we have. The idea is the same. Forward body bias the critical path to make it faster. Ignore the power that you are expending, and reverse body bias the non-critical path transistors. Then what will happen is, when you are reverse body biasing it, you will save power. Another idea is the idea of a drowsy cache, because up till now we were kind of dealing with generic in-circuit elements, right? We were not dealing with memory elements. So drowsy caches, we will define a normal, so caches typically have a normal operating mode, we'll define a drowsy mode. So let's say if the VDD is 1 volt, right, which is typically the case these days, you will have a row of SRAM cells and you can read, write, do everything. It is possible for me to reduce the supply voltage to a value where I can't read or write. The voltage is not sufficient to read or write, but I can still maintain the value and I will not make any mistakes. I will not lose any value. A 0 will not become a 1, a 1 will not become a 0. This is a neat idea. It's a neat idea. Why? The reason being that we are reducing the voltage to reduce the amount of leakage. So this is just to reduce leakage. We are reducing the voltage to reduce leakage power, right? But we are not making mistakes because we are not reducing it so much that the cell loses its value. We are only reducing it to a level where it will maintain its value but will not be operational. You can't read or write. You want to read or write, increase its voltage back again. So this is a drowsy mode where you're not sleeping, you're just drowsy at 0.3 volts. You can maintain the value but not access. And the great idea is here that it takes 1 or 2 cycles to either enter or exit the drowsy mode. So we treat a set of cache lines as one unit and we can turn it on and off as one unit. So we don't want to do it like cache line by line, but maybe like at the group of several lines, 16 lines, 32 lines. And once a set is turned on, we don't want to turn it off, turn it on very frequently. That would kill our performance. That would induce a lot of voltage transitions. Voltage transitions make the power grids unstable. They draw in a lot of current, which also dissipates power. So we will need an architectural mechanism to basically predict in the future what would the accesses look like. We will take temporal and spatial locality into account and then decide what part to put in drowsy mode. The circuit looks like this. This is not very tough as a circuit. So we have in fact seen this. So we have seen this circuit. This is a inverter pair. These are the word line transistors. So we have seen them, right? So this is not something that we have not seen. So this is the drowsy signal. So let us see what happens if the drowsy signal is 1. If the drowsy signal is 1, then what happens is that the word line enable basically becomes 0. So that is how our logic is, that if the drowsy signal is set to 1, then the word line enable here, we make it 0. So what would this mean? T1 is on, so let's say this is on. T2 is off because this is 0. And T3 is on. Why is T3 on? Well, let's see. So this is 1, so this voltage here is 0, so this is 1. So the T3 is on. If T3 is on, let's look at this value. This is the in the reverse of this. This value is 1, inverse is 0, T4 is off. So if T4 is off, then essentially this gate is open. So VDD low goes here and this becomes the power line. Okay, so this goes to the power line over here. So this is the circuit diagram. So what basically happens is that your power line becomes VDD low. On the other hand, if let's say the drowsy mode is off, let us see what happens. Then this would be 0, your word line enable will be 1. So if this is 1, then this signal here is 0. This is 0. The inverse is 1. Then this is 0. This is 1. Because this is 0, this transistor is not conducting. But because this is 1 here, the output would be VDD. Given the fact that the output would be VDD and this is 1 over here and word line enable is 1, your word line enable in this case would be 1. So what would happen is that your word lines would get enabled when the power is equal to VDD. And in the previous case, when this was actually 0, the output would have been 0. So when your power would have been equal to VDD low, which was the previous case, this value here would be 0. So which basically means that when my word lines are enabled and my circuit is operational for reading writing, I have full supply voltage. But when my word lines are not enabled and my circuit is not enabled for reading writing, I have a lower supply voltage which is VDD low. At this point of time, I cannot access it, but I can still maintain the value, which is exactly what this circuit over here is showing. So we have discussed power management. We'll now spend a very short amount of time discussing temperature management, because in general reducing power is tantamount to reducing temperature. Sometimes we can do more. So the question is, how do you measure temperature? That's very hard, because on a chip you have a spreader, heat sink, everything. So what we can do is we place thermal sensors over the chip. A thermal sensor is nothing but a bunch of diodes, and the transition time of a diode is dependent on the temperature. So what happens is that you take a sequence of diodes and you measure their transition time using another clock, another circuit. Based on the time, you try to infer the temperature. So what happens is that in general our temperature remains okay, but sometimes you can have these temperature hotspots. You can always do DVFS, static power reduction, fetch throttling. Stop and go is again a simple technique, where if a core is getting very hot, just stop it, let it cool down. Then you can do what is called heat and run thread assignment, which is don't allow two hot cores to be close to each other. Because then what will happen is there will be lateral heat transfer and they will get heated up even more, because if there is a heat transfer, leakage will increase, that will increase temperature, the leakage temperature feedback. So what you do, at least what a good scheduler, OS scheduler should do, is that it should read the temperature from the on-chip temperature sensors. If a thread's activity is increasing, its power will increase, so you move it to a colder region of the chip, because leakage is a slightly nonlinear function of temperature, so you don't want this feedback to set in. Moment you have more activity, you move it to a corner or space out the cores. So I have a diagram here. If let's say there is a lot of hot regions here, dark means hot. So what will happen is that they will kind of mutually transfer heat and then they will transfer heat sideways. So you'll have a full hot region. Instead of that, just take both the hot cores and place them far away. So their heat transfer will be limited, but that nonlinear leakage temperature feedback loop is not kicking in. Hence, what is happening is that overall things in our chip are cooler than the earlier case. So again, don't have two hot cores nearby. Lateral heat conduction leads to the leakage temperature feedback loop, which is slightly nonlinear. If a large hotspot forms, a spreader will find it hard to dissipate heat, even though it does a good job, but its capabilities are limited. Typically, what would happen is that we have a temperature on the, a constraint on the peak temperature. right? Or we define something as the TDP, thermal design power, is the maximum amount of power that the chip can dissipate before reaching a temperature cutoff. So the idea is that even when the total power is much lower than the TDP, hotspots can still form, which is why the hardware's hand will be forced to bring in DVFS. But again, with proper scheduling of the jobs, a lot of this can be managed. So this is the last slide. This is something that we always love to look at. So let me just quickly summarize. The major power consumption mechanisms are, of course, dynamic power, leakage power. Short circuit power can come in this. Dynamic power is purely a function of the number of transitions, and leakage power is a function of many things. The number of interfaces that are non-ideal, the current conduction mechanisms in them, and also things like the supply voltage, body bias, and other things. Temperature modeling is tough, but it's not very tough as we have seen. We looked at the Fourier's heat conduction equations and how they generalize to the finite difference and finite element methods, and how the Green's function fundamentally changes a quadratic problem to linear. Power consumption again can be reduced using a combination of DVFS, clock gating, power gating, throttling. And there are a few bespoke mechanisms as well, such as Drowsy caches for reducing leakage power. So given that we have looked at power and temperature very deeply and very thoroughly in this section, we will use these concepts going forward to the next chapter, where we will discuss reliability, which is very heavily dependent upon what we have thought and discussed in this chapter. So see you in the next chapter.